Hello everyone, my partner and I will introduce you the applications of triple integrals. This video is quite simple, so it's friendly to beginners. Now, let's get started. Triple integrals help us analyze three-dimensional spaces with the quantities within them. Imagine a 3D region, let's call it region B, with a function that describes some property across that space, like density, heat, or energy. To work with this, we use a tiny volume element called dV, which changes based on whether we're using rectangular, cylindrical, or spherical coordinates. Fubini's theorem tells us that if a function is smooth and continuous over a rectangular box, say, with x between a and b, y between c and d, and z between r and s, then we can compute the triple integral step by step. We can integrate in any order, first with respect to z, then y, then x, or any other sequence. So, here comes the first example. Find the volume of a cube where x, y, and z each range from 0 to 1. How do we solve it? Well, the volume is the triple integral of 1 over this region. First, integrate with respect to x from 0 to 1. The integral of 1 with respect to x is just x. Evaluate from 0 to 1, which gives 1. Next, integrate with respect to y from 0 to 1. The integral of 1 with respect to y is y. Evaluate from 0 to 1, which again gives 1. Finally, integrate with respect to z from 0 to 1. The integral of 1 with respect to z is z. Evaluate from 0 to 1, giving 1 once more. Multiplying these together, we get our final result, which is the volume of the cube is 1 cubic unit. The next example is the volume of a cylinder. The problem is we want to compute the volume of a cylinder with radius 1 and height 2. In cylindrical coordinates, we describe points using r, which is radius, theta, which is angle, and z, which is height. The volume element here is r times dr, d theta, and dz. The limits are r goes from 0 to 1, theta goes from 0 to 2 pi, and z goes from 0 to 2. Then we do the integral. First, integrate with respect to r from 0 to 2. The integral of r with respect to 2 is 1/2 times r squared. Evaluate from 0 to 1, giving 1/2. Next, the integral of 1/2 with respect to theta is 1/2 times theta. Evaluate from 0 to 2 pi, which gives pi. Finally, the integral of pi with respect to z is 1 pi times z. Evaluate from 0 to 2, which gives 2 pi. Then we have our final result, which is the volume of the cylinder is 2 pi cubic units.
Next, find the volume of a sphere with radius capital R using spherical coordinates. In spherical coordinates, we use R, distance from center, theta, azimuthal angle, and phi, polar angle. The volume element is R squared sine phi times dr, d theta, d phi. So the limits are r goes from 0 to capital R, theta goes from 0 to 2 pi, phi goes from 0 to pi. First, integrate with respect to r from 0 to capital R. The integral of squared root with respect to r is r cubed over 3. Evaluate from 0 to capital R, giving capital R cubed over 3. Next, integrate with respect to theta from 0 to 2 pi. The integral of capital R cubed over 3 times sine phi with respect to theta is capital R cubed over 3 times sine phi times theta, evaluated from 0 to 2 pi, giving 2 pi capital R cubed over 3 times sine phi. And finally, integrate with respect to phi, which is from 0 to pi. The integral of 2 pi capital R cubed over 3 times sine phi with respect to phi is negative 2 pi capital R cubed over 3 times cosine phi, evaluated from 0 to pi. This simplifies to 4 pi capital R cubed over 3. So the final result, the volume of the sphere is 4/3 pi capital R cubed. One day, after meticulously tidying her beloved hat, Herta accidentally straightened it. The once curved and elegant shape transformed into a tall, symmetrical structure, something that could be modeled by the equation. In other words, the hat has become a solid bounded between 0 and 10, with each horizontal cross section forming an ellipse that changes size with height. Our goal to calculate the volume of this new straightened version of Herta's hat. First, let's understand the shape. The hat's sides curve in particular way that follows this rule. 16 times the distance from the center squared equals the height minus 10 all squared. To find the volume, we will use cylindrical coordinates which measure the distance from the center. We will call this r. The angle around the hat, theta, going all the way around from 0 to 2 pi. The height of the hat, z, from the base at 0 to the top at 10. At any given height, the hat's width changes. Near the top, which is z close to 10, the hat gets narrower, while at the bottom, z close to 0, its width wider. Specifically, the maximum width at any height is 10 minus z divided by 4. Now, let's do the calculation step by step. First, we look at small slices of the hat. For each tiny pieces, we calculate r times dr, a small change in width from the center out of the edge. This gives us 10 minus z squared over 32 for each height. Next, we add up all these slices from the base uh, 0 to the top 10. This gives us 1000 over 96. And finally, we account for the full circle by integrating around the hat from 0 to 2 pi. This gives us our final answer. After doing all these calculations carefully, we find that the volume of Herta's hat is 125 pi divided by 6. This means if we were to fill the hat completely, it will hold exactly this cubic units of whatever we put inside. Whether that's tea, magic potions, or whatever else Herta might keep in her hat. Finally, here comes our final question. The power core of the Astro Express is modeled as a spherical energy cloud. The energy density within the core is not uniform. Instead, it decreases exponentially with distance from the center. The density function is given by the equation. The region of interest is a solid sphere of radius 3 centered at the given point. Compute the total energy stored in this spherical region. Okay. So the core is shaped like a perfect sphere with a radius of 3 units centered at a point that's 3 units above the origin. To describe points in this sphere, we use spherical coordinates with r measuring distance from the center from 0 to 3, phi measuring the angle from the top from 0 to pi, and theta measuring the angle around the sphere from 0 to 2 pi. The energy isn't uniform. It's strongest near the center and follows the a specific pattern based on position. The density depends on the square distance from the center, a term involving the cosine of the polar angle, a constant value of 9. All of this gets squared to give the final density at the point. So we written down this equation and we just need to finish the calculation and finally we can get the answer. Since we have done many equations, I won't elaborate the way I did it, so I wrote down my equations. You may pause if you want to take a look. So this is the end of this video. Thank you.